Hello everyone, welcome back. This is part 3 of the thermodynamics series, and in this part we're going to be talking about Gibbs free energy for the first time. We're going to calculate Gibbs free energy predicting spontaneity by using delta H and delta S that we've already covered, and then we're going to calculate standard changes in entropy. So Gibbs free energy, you have to know what the Gibbs is in order to fully know whether something is going to be spontaneous or not. And so Gibbs free energy is basically the maximum amount of work energy that you're going to be able to release to the surroundings, or the amount of work you can do by the system, okay? And that's making sure that you're keeping pressure and volume constant. All right, and so it's often called chemical potential because it's analogous to what you've got stored in those chemical bonds. So the delta G of the system is equal to the delta S of the system, the enthalpy change, minus the temperature in Kelvin times the change in entropy. And remember, watch your units on these because S is joules and delta H is kilojoules. All right. So the delta S of the universe is positive when something is spontaneous. And so delta G is typically negative. Okay, so delta G is typically negative. And so I've got a little table here to kind of show you how this works. And then on the next slide, though, I'm going to go ahead and change. I've got it blown up for you. All right, so when delta G is negative, it's spontaneous. So that is your key. If you do this calculation and you get a negative delta G, then you know that this is going to be spontaneous. And so here is kind of what you look at. So, and remember, this is in kilojoules and this is in joules. So this delta H is going to be the bigger number. All right. So when H is negative and S is positive, it's spontaneous at all temperatures. So it's always spontaneous. If your delta H is positive and your entropy is negative, it's always non-spontaneous at all temperatures. If you have both of them negative, then they're spontaneous at low temperatures, and if both are positive, it's spontaneous only at high temperatures. So that's what you got to remember. So if the delta H is, if you've got a negative positive, it's spontaneous at all temperatures. Okay? If it's positive negative, it's non-spontaneous at all temperatures. If both are negative, it's low. If both are positive, it's high temperatures. So this is very, very much associated with what the temperature is that you're looking at. So if you have a reaction of carbon tetrachloride going to graphite and chlorine gas, the delta H, and so this is how you know you're going to be using this Gibbs free energy, okay, calculation, which was the delta G is going to be equal to the delta H minus T delta S. Okay, so you'll know that because you're given a delta H and a delta S. Okay, and so I want you to calculate the delta G at 25 degrees C and see if it is spontaneous or not. And so in the first part of this, the delta G is equal to delta H minus T delta S. All right, now you got to make sure that you change one of them, okay? So we know T is going to be 273 plus 25 equals 298 Kelvin. You know, and I'm just going to change the delta H, okay? Delta H is 95.7 kilojoules. So times 1,000 joules per kilojoule. So that's equal to 95,700 joules. Why did I do that? Because my delta S is 142.2 joules. per K. Oops, sorry. All right. So the delta G equals delta H. So that is then once I've got this figured out and I've got my units the same, it's 95,700 joules minus 298 times 142.2 joules per K. All right, and that's K. So the K's will cancel. And so that is going to give me 95,700 joules minus 42,400 joules equals a positive 53 joules, or 53.3 kilojoules. Since this is a positive number, it is non-spontaneous. Now the second part of this is interesting. Okay, the second part of this says if it's not spontaneous at 25, which we just showed it wasn't because it had positive, at what temperature, if any, will the reaction become spontaneous? So I'm looking at that and I have a positive, positive. So that should be spontaneous at high temperatures. So what you do is you set delta G to 0, okay? So because anything lower than that is going to be a negative number, right? So then I can solve for T. So 0 equals delta H minus T delta S. 0 equals, I already know these numbers, 95,700 minus T times 142.2 joules per K. All right, and this was joules. So rearranging for T equals 95,700 joules divided by 142.2 joules per K, and that's going to give me 673 K. So anything above 673 K will be spontaneous. So that's how you figure that out. And then I give you some kind of things to think about in that practice question as well. All right, so we've talked about standard states and about forming things from their standard states. Gas, 1 atmosphere. Solids, liquids, its pure form at 1 atmosphere pressure and temperature of interest, which is usually room temperature. And solutions will be at 1 molar. The third law of thermodynamics is one we haven't seen before, and it states a perfect crystal at absolute 0 has an enthalpy of 0 joules per mole K. Every substance that's not a perfect crystal at absolute 0 has at least some movement. Okay, it has some entropy. And so the absolute entropy of substances is always positive because they've always got some entropy. This is the only time you have no entropy, and that is a perfect crystal at 0 K. There's only one way to arrange it. So in a process that we're looking at this, the final condition is more random than the initial condition, and so that's why it's always positive. So the entropy change is favorable for spontaneous. For the process in which the final condition is more orderly, then the delta S is negative, and it would be unfavorable to have that. And so what we see is that then the system change in entropy is equal to that in the reaction, which is going to be the sum of all the product's entropy minus the sum of all the reactant's entropy. And we've seen this. This is where you use that standard. And we did this for delta H. And you can do the same thing for delta S, and actually we'll see you can do the same thing later for the delta G. So S designates standard state because it's got that little 0 there. Since it's an extensive property, it depends on how much you have. So the entropies for 1 mole of substance at 298 K will be typically what you're given in a chart. Don't forget that it's in joules per mole. Gas states, just like we saw before, has a larger entropy than liquids, and liquids has a larger entropy than solids. And this is just a table of the different types and different levels of entropy in gases, liquids, and solids. Also, as we've said before, the larger the molar mass, the larger the entropy, because you have more pieces that could go together in different ways. The more complex, the larger the entropy. Dissolved solids typically have larger entropy than in their solid form. So the standard entropy change is the difference between the products and the reactants. And this is worked exactly like we saw the delta H, but the absolute entropy of anything is always positive. So you're not going to have zeros like you did in the enthalpy for elemental state things. Everything is going to have enthalpy and entropy, and it's all going to be positive. So in this particular one, it wants you to figure out the delta G. Need to skip. Okay, the delta S, sorry, for the balanced chemical equation. Okay, and I have a chart here with the values, which you'd have to be given, right? And so, as I like to do, I'm going to write my numbers underneath. 192.8, and these are all joules per mole K. 205.2, 210.8, and 188.8. So in entropy, they all have entropy. Like if we were doing delta H, that O2 would be a 0, right? But in entropy, they're going to have a number associated with them because they're not a perfect crystal at 0 Kelvin. And so for me to calculate this, the delta S0 of the reaction is I'm going to calculate it from the delta S0 of the products minus the reactants. So delta S0 of the reaction is going to equal 4 times 210.8, okay, plus 6 times 188.8 minus, because that's my products, minus reactants, 4 times 192.8 plus 5 times 205.2. All right, so that's products minus reactants. Just like we did the delta H, except the only difference is that we have numbers associated with everything. So 843.2 plus 1132.8 minus 771.2 plus 1026. I do all the steps just because I don't want to miss anything, and I just want to make sure when you're putting your stuff in the calculator that you're actually doing what you're supposed to do. You don't want to miss points because of a calculator error. And so what I end up with is a positive 178.8 joules per K for my delta S. All right, so same exact procedure that we did in the delta H, you're doing for a delta S, okay? And it's because it's the standard entropy changes, okay? And there's one to practice. And that's it for part 3.